Hi students, welcome to Physics for Everyone classes. This is your satish. So in this section we can see one of the very important concept from the chapter rotational motion, which is there you can see pure rolling after a pure sliding, which means initially we are throwing an object. What kind of object it is? A rolling body. Either you can take it as a solid sphere or a hollow sphere or a cylinder or a disc. So whatever maybe it is, we are throwing it on the rough surface with initial linear velocity v0. There you can see initially this body does not have any angular velocity. We are just throwing it on the rough surface. After traveling certain distance, certainly the object attains a pure rolling motion because of the frictional force. Suppose if there is no friction, how much the linear velocity initially we were given, the object moves continuously with the same linear velocity. It does not acquire any angular motion. So the angular motion is because of the frictional force. And you can see the situation at t is equal to 0, we are given this velocity. And after some time, at t is equal to t dash, this object attains the pure roll. You can see the condition, 0 is less than or equal to t is less than t dash. So what kind of motion here is? Pure sliding. There is no, the object is sliding. We can see, and continuously the object acquires some angular velocity, but it does not satisfy the pure rolling condition, which is v is equal to r omega. At the time t is equal to t dash or more than that, the object attains the pure rolling. Then we have assigned questions here. At the time of pure rolling, how much the velocity acquired by the object? Then we have three important formulas here. The one gives you after attaining the pure rolling, the velocity expression you can see how much it is, v0 divided by 1 plus beta. As you know, v0 is the initial linear velocity. 1 plus, what is beta? So beta is a constant. When we are dealing the rolling motion, as we know, beta is defined like this. It is k square divided by r square, where k is the radius of gyration of the given object and r is the radius of the object. That we can get this beta value if we know precisely what kind of object here is. For example, if it is a solid sphere, the value of beta is how much? 2 by 5. Hollow sphere, 2 by 3. For the disk, beta is 1 by 2. And the angular velocity attained by this object, when it attains the pure rolling, you will get, after getting v, omega is equal to v by r. Omega is equal to v by r. There you can see the same expression. So one more term you will get, which is divided by r. So v0 by 1 plus beta into r. And after how much time this happens? Then we have the formula t is equal to v0 by mu g into beta by 1 plus beta. So these three formulas which are really matters while we are dealing the questions from JEE or the NEET questions, because we have a very less time to get the result. So please remember this results. How we should get the expressions at the time of pure rolling, how much is the linear velocity, angular velocity, and a time taken for the given object to attain the pure rolling motion. Let us start. Here we have two methods. One, we can use the kinematic equations, or else we can use law of conservation of angular momentum. If we use the conservation of angular momentum, we can easily get the velocity acquired after a certain time. After getting the velocity, you'll get the angular velocity as well as the time taken by it. So here, I'm applying conservation of angular momentum about the bottommost point. Here you can see the point of contact. Before that, so initially tell me in which direction here the frictional force acts. There you can see this is the point of contact. So here is the object and it has got a linear velocity. How much initially? V0, where angular velocity is initially 0 and P is the point of contact. There you can see. So this point is in contact with the ground. Here you can see this is the ground and here is the ground. Now you need to just look at this point. So what is the tendency of motion of this point? It is very clear as the whole object is moving in the forward direction. The tendency of motion of this point of contact is also in the forward direction. And where the frictional force always opposes the tendency of motion. So what is the direction of tendency of motion? Forward. And the frictional force opposes the tendency of motion. So there you will get the frictional force direction in the backward. You can see this is the direction of frictional force. So what kind of friction it is? Here it is the kinetic because the object is in motion. There you can take it as Fk. And you know the formula for kinetic friction. According to laws of friction, you can write directly. Fk is equal to mu into normal reaction, where n is equal to weight of the object because it is on the plane surface. We got kinetic friction there. So here the object linear velocity is gradually decreases. So this velocity V0 gradually decreases because of this retarding force. So how much is the retardation there? So there we can see the retardation A is equal to mu into G because A is equal to net force divided by mass F divided by M, which is equal to the frictional force. We got it as mu mg divided by m. M and m get cancelled. You will get the retardation experienced by this object. How much? Mu g. So with this retardation, this velocity is gradually decreasing. At the same time, about the center of mass, you can see this object is going to rotate. In which direction? In the clockwise direction. Because about this point, this frictional force provides the torque, and that torque gives the angular velocity for this object, omega. So there you can see clearly this linear velocity decreasing and angular velocity is increasing as the time progresses. As the time progresses, we can expect about this point of contact, the condition V is equal to R omega. Here you can see V is the linear velocity acquired after a time t dash, and omega is the angular velocity, and R is the radius of the given object. If the condition satisfied about this point, then we can see this point of contact is instantaneously at rest, or nothing but the object is performing a pure rolling motion. As you know, in pure rolling motion, the frictional force will be vanished. So there we can expect the frictional force, which is the kinetic friction, which is existed for the time t is equal to 0 to t is equal to t dash. It provides the pure rolling motion here. Now the time to get all the three results. So as I mentioned, we need to use law of conservation of angular momentum about one particular point to get the linear velocity at the pure rolling motion. So let us see how to apply the conservation of angular momentum about the point. Now tell me, which point we need to select here? There is a condition. For to apply the conservation of angular momentum about that point, the net torque acting on it should be equal to 0. Suppose if we select the center of mass as the point, and then we have what? We can see this is the center of mass, and we got here the frictional force, kinetic friction is there. If we choose this point for to apply the conservation of angular momentum, it's not possible because about this point, there we have got an external torque because of this kinetic friction. So which point we need to select where the net torque acting on the object is equal to 0? Here, the point of contact. So about this point, let us take conservation of angular momentum. So because this frictional force is passing through this point, the torque by this frictional force comes as 0. And one more force is there, which is the weight of the object, which is always acting from the center in the downward direction. And this is also passing through that point. Because of these two forces, the torque comes how much? 0. There is no net torque about the point of contact. So we got the point. So let us see the situation. So here initially how much the velocity? V0. Angular velocity how much here? 0. Initial angular velocity is 0. We have got frictional force. And after a time t is equal to t dash, this object has got a linear velocity v, and the angular velocity is how much? Omega. The angular velocity is omega. And here the condition is v is equal to r omega. The pure rolling condition is satisfied. V is equal to r omega. Now write down conservation of angular momentum about the point of contact. So initial angular momentum is equal to final angular momentum. So tell me, what is the initial angular momentum here? About this point. Here is the point. So about this point, this object has only translational motion. Directly we can write the formula for angular momentum is mvr. So m, velocity is v0 and radius is r, which is equal to, what is the final angular momentum? Because the object is in pure rolling motion, it has got two angular momentums. One is linear angular momentum, which means because of the translational motion it has got the angular momentum. Then we can write it as mvr, and due to rotation the angular momentum is I omega. So it is the sum of these two. There you can write I omega is the angular momentum of this object about the center of mass. You see, about the center of mass, always the object has only rotational motion. But about the point of contact, it has got the rotational motion as well as the translational motion. So I omega is the angular momentum about the center of mass plus the angular momentum of center of mass with respect to the point of contact. How much it is? mvr, because it has got a velocity and whose perpendicular distances are about the point. Here you can write mvr. You see, initial angular momentum is mv0 into r is equal to I omega due to rotation plus mvr due to translational motion. From here, we need to find v value. Now you can write I, because we don't know precisely what object is given there. So this is the reason we can take I is equal to m into k square. So write down. So m v0 r, which is equal to m into k square. We can write it for any kind of object. M into k square, where k is the radius of gyration, into omega. How you can write omega? V by r. Under this condition, V is equal to r omega. So V by r plus, you can write here, plus mvr. mvr. Here you can see few terms will get cancelled. One is mass on both the sides, and I can write here r is also get cancelled, but here r is not there. I can take it as r square. Therefore, V is equal to, if I take common here V in this equation, the first term comes as k square by r square plus 1, and here it is, this is V naught. Therefore, V is equal to V naught divided by 1 plus k square by r square. We can write it as beta. So where beta is equal to the ratio of k square by r square. As I mentioned, if it is a solid sphere, the value of beta is equal to how much? 2 by 5. Suppose if I am assuming it as a solid sphere, you need to take how much beta? 2 by 5. So which is equal to V naught divided by 1 plus beta, you can take it as 2 by 5, which is equal to 5 into V naught divided by, you can see 5 plus 3 is 7. How much you got the result? At the time t is equal to t dash, this solid sphere attains the pure rolling motion. At that time, it has got the velocity, how much? 5 V naught by 7. Will you get the same result here for all kinds of objects? No. Here you can see it depends on this factor. If the beta is very small, as of course, beta is very small for only the solid sphere. If this is very small, and suddenly you get the value of the velocity will be larger, because both are inversely proportional. Out of the 4 objects, if you are taking the solid sphere, hollow sphere, or a disc, or a solid cylinder, out of all the given objects, the beta is minimum for a solid sphere, which is 2 by 5. When this is smaller, you will get certainly the maximum linear velocity at the time of pure rolling. So you need to remember this result, which is very important to get the final linear velocity at the time of the pure rolling. V is equal to V naught divided by 1 plus beta. After getting linear velocity, just by dividing this expression with the radius, you will get the angular velocity. How much it is? There you can write. Omega is equal to, angular velocity is equal to V upon R. You got V is this much. So V divided by 1 plus beta into R. So this comes as the angular velocity at the time of pure rolling. So at the time of pure rolling, how much is the frictional force? It comes as 0. If the frictional force is there, continuously omega gradually increases, it doesn't satisfy the condition V is equal to R omega. Isn't it? Yes. And we have got V value, we have got omega value. And at last we need to look at after how much time this happens. Let us see that also. So we have got the results with us. Please remember V value, omega value, and retardation of the object also. And we applied it for the solid sphere. Now, after how much time this object acquires the pure rolling? Let us see. For this, we need to suddenly use the kinematic equation, which is V is equal to U plus AT to get the time. So what is the final velocity at the time of pure rolling? We got the result. How much? It is V naught divided by 1 plus beta. Just now we completed it. what is your initial linear velocity, which is v naught. Because of the kinetic friction, the object is slowing down with a retardation, which is how much mu g. We also got this. So a is mu g into time t dash, and with this you will get so mu g into t dash. If it comes to this side, which is equal to, take this term to the side and take v naught common here into v naught taken common, 1 minus this expression 1 divided by 1 plus beta. Just we are taking these terms mu g into t dash to this side and this whole term to that side and taking common v naught. And t dash is equal to v naught upon mu g into, and take the LCM of 1 plus beta here, and the numerator you will get 1 plus beta minus 1. There you can see 1 and 1 get cancelled out. And I got t dash is equal to v naught by mu g into how much? Beta divided by 1 plus beta. So there we got the expression for the time also. And keeping beta how much? For the given object, if it is a solid sphere, beta is how much? 2 by 5. Right now, for a solid sphere, beta is equal to 2 by 5. The time taken is v naught by mu g into 2 by 5 divided by 1 plus beta. 1 plus 2 by 5, which is equal to v naught by mu g into, you can see if you have taken 5 LCM here, 5 get cancelled, and 5 plus 3 is 7, and finally you get 2 by 7. So after this time, v naught by mu g into 2 by 7, after this time, this solid sphere attains the pure rolling motion. You can see, if you choose the object is a solid sphere, in very less time compared to the other objects, it will acquire the pure rolling motion. At that time, the object has the maximum linear velocity, in the sense comparing to the other objects' velocities, it has got the more velocity at the time of pure rolling. So we are comparing the solid sphere with the other objects like a hollow sphere whose beta is equal to 2 by 3, and a disk whose beta is equal to 1 by 2, or a solid cylinder whose beta value is equal to again 1 by 2. So by comparing all these different shaped objects, if you choose a solid sphere, in a less time it acquires the pure rolling motion.